देखिए, इसको क्या करना है, इस पर नहीं आ रहा है ना। तो
Sir, we welcome you. Please start the session, sir. So, sir, Ramnaresh Sai. Dear all the participants, we welcome to this session by eminent speaker, Professor Ramnaresh Rai, sir, from NIT Agartala. Hello. Yes, sir, please.
Yeah. Good morning to everyone. Today we are going to discuss on materials for hydrogen storage system. You all are aware the hydrogen is very important nowadays, and it is a source of energy. We all are aware there are a source of energy is a coal, then the steam is the one, and electricity, and these are having the certain limitations, and which is going to be a over once maybe 100 years or 200 years, or it's having a certain life period, thereafter it will be exhaust. So we all researchers are working in the area, so in such a way that we will work on the renewable energies. Under that, we have seen that solar energy is one, wind energy is another, and further the people are working on the area of to have the hydrogen is also another source of energy. As in India as well as in the foreign countries, we have observed and we have listened through the newspaper and all that nowadays buses are running with the hydrogen. So this fuel cell is very important, which will produce a lot of energy to run the any engines. So, but the problem is this hydrogen can be stored, but storing this energy, hydrogen energy, is not so easy. It is a really complex process, and for that we have to design a materials. As an engineer, as a researcher, we have to focus on in such a way that we have to design the materials so that hydrogen can be stored and it can work as a fuel. We all are aware when we are traveling with a car, every 10 kilometers or the 5 kilometers, we will find that petrol pump where the petrol is about to exhaust, you are going to refill it. Similarly, if the hydrogen can be stored and it can be refilled like this, similar way or some other way, then it will be a more economical and more feasible, and it's have the lot of potential, and its output will be much better compared to the other source of energy. So our presentation is in the form of introductions, hydrogen storage methods, material requirements for the hydrogen storage. There are many challenges how to store this energy, and it's have the advancement and innovations. It's have the future prospects as well as the applications and conclusions. So these are the layout of our presentations. Once we'll talk about the introductions, already we have discussed, and before discussing about the introductions, why we are focusing on this, why it is so important, where it's have the applications. These are the prime area. Based on that, one can think of it, one can design of it, the hydrogen storage systems. So many applications are there. We will see one by one. So now hydrogen storage is crucial for clean energy. Moreover, this energy is a very clean energy. Like we have the wind energies or the solar energy. Similarly, this energy is a very clean energy. Materials play a pivotal role in enabling the efficient hydrogen storage systems, and this presentation will explore the various materials and their significance. Hydrogen storage methods. The choice of a storage materials and method depends on the factors like safety, energy density, application specific requirement. So based on the applications and then its energy densities and the safety, we have a different types of storage systems. One is this hydrogen gas can be stored in the form of compressed gas. It can be stored in the liquid hydrogen storage, something like in a cylinder and all. Then chemical hydrogen storage in the form of chemicals, and immediately spontaneously it will release the energies. The solid state hydrogen storage, it may be in the solid state also. Carbon nanotubes. So if you use the carbon nanotubes, we can store the energy over there. Then porous materials. In the porous materials also, we can store which can be helpful for the storage of hydrogen energies. Sometimes, like a petrol pump, we are having the underground tank. Similarly, here also it can be possible, but we have to design in such a manner that underground storage is also possible. So each method has unique characteristics, advantages, and limitations. And understanding these methods is crucial to appreciate the role of materials in optimizing hydrogen storage systems. However, ongoing research, many researchers are working, many engineers are working in India as well as in the abroad. And they're exploring the way out to have that or to develop the new materials and the technology for more efficient hydrogen storage. So hydrogen can be stored in an efficient manner. So compressed gas storage. Storing hydrogen at high pressure, 350 to 700 bar, it is very, very high pressure. It is especially designed tanks is one of the smallest, simplest process, and carbon fiber reinforced composite materials are used for making these tanks. Liquid hydrogen storage. Say hydrogen can be liquefied at extremely low temperature, cryogenic temperature, about minus 253 degrees centigrade, and stored in a cryogenic tank. So this is another way. Chemical hydrogen storage. Hydrogen can be stored in the chemical compounds like ammonia or liquid organic hydrogen carriers. These compounds release hydrogen through chemical reactions as and when needed. So this is the one way of storing. Solid state hydrogen storage. That means it is also called as a metal hydrides. So these hydrides will help you to release the energy as and when required. So certain metals such as magnesium or titanium can absorb and release the hydrogen gas when heated. And this is a reversible process, making it suitable for on-demand release. The carbon nanotubes. Nanomaterials are play the very important roles. And if you are talking about the tubes, means nanotubes, you can see the gap of the tubes, and those tubes are used for storing of the hydrogen. So these nanomaterials can absorb the hydrogen molecules, potentially providing the high density storage. Carbon nanotubes or the other porous materials for observing the hydrogen molecules. Heat exchangers is also required for the temperature control during the absorptions as well as desorptions as and when needed. Porous materials like metal organic framework MOF and covalent organic framework are porous materials with high surface area, making them suitable for hydrogen absorptions. We'll talk about the underground storage. Hydrogen can be stored in underground. Salt caverns, and depletes natural gas reservoirs. As we have seen, the natural gas are also having the certain limitations, and after a certain period of time, that will be also over natural gases. So hydrogen R can be stored in similar fashions, and it can be released as and when required. So wellheads and piping for injections and extractions of the hydrogens, safety measures to prevent leaks, and monitor storage integrity. So you can see that one graph which I am presenting it. By seeing this, we can see that the theoretical capacity storage of the hydrogen, if it is a carbon nanotubes or the some other base. So we'll see the if it is a steel cylinder where you want to store this hydrogen, this is the watt hour per kg. So you can see that if it is a carbon tubes, nanotubes, then 10,000 watt hours per kg of the hydrogen can be stored. But if you store in the cylinder, you can see that it is around 1 or so. If you see the composite cylinder, hardly you can go for the 2. If you have the liquid hydrogen, then it is up to the 4,000. And if it is the primary hydrides form, then again it is up to the 2,000 watt hours per kg. So we can see that the technology has developed in such a manner, and now the people are working on the carbon nanotubes, which is used for storage of the hydrogen. And there you can go for around 11,000 watt hour per kg. You can imagine that how much it will be helpful to store the energy, and as and when it's released energy, and that can be used for movement of the vehicles in industries, in petrochemicals, wherever they have the applications. Now, if we talk about the requirement of the materials, or we can say the properties requirement for the materials for storage of hydrogen, efficient hydrogen storage materials must meet the specific criteria. Certain criteria it has to meet. What are those? They should have the high hydrogen capacity, ensure fast hydrogen uptake and release, exhibit thermodynamic stabilities, and be reversible for practical applications. These materials requirements are fundamental in achieving effective and sustainable hydrogen storage systems, which we will discuss in the next presentations. The encouraging hydrogen storage materials in carbon nanotubes, since their synthesis in pure carbon nanotubes below the 1% of the hydrogen can be observed. So this can be stored in the compressed gas storage. So compressed gas storage is one of the methods for hydrogen storage. Materials like carbon fiber composites, metal hydrides are commonly used. This method stores the hydrogen gas under high pressure, and it has advantages like already I have discussed in the graph, and there you have observed. So very high amount of the carbon can be stored if you are using the carbon fiber composites in the form of nanotubes. Understanding the materials involved and their characteristics is essential to grasp the effectiveness and the limitations of the compressed gas storage systems. High pressure tanks made of materials like carbon fiber and forced composites or high strength steels. High strength steels is also can be used to make the high pressure tank, and there it can be stored. Pressure relief devices such as safety valves, fittings for gas flow controls. So these are to be added, and which will take care of the safety. Liquid hydrogen storage involves storing hydrogen in its cryogenic liquid form. Materials like a specialized tank and insulations play a pivotal role in the maintaining extremely low temperatures. So you can see in the figures, here is tank, and in the tank inside, we're providing the insulating materials so that it will maintain the properties of the hydrogen gas, which is used for source of energy. This method offers high energy density. See, as it is have the very high density, storing is not so easy. It is a challenging. So accordingly, we have to design the cylinder, or not cylinder, we can say the tank, so that it can sustain the certain pressure, and it will help us. It should not be dangerous for us. Hard drives chosen for storage applications provided low reactivity, that is high safety, and high hydrogen storage densities. Leading materials are the materials which are used nowadays, that is the lithium hydride, sodium borohydride, lithium aluminum hydrides, and ammonia boro. That is next is the chemical hydrogen storage. Chemical hydrogen storage is a method where hydrogen is chemically bonded with the materials, typically a chemical hydrides. This technique allows for high density hydrogen storage, which can be released through controlled chemical reactions. Understanding the materials and their chemical process is essential to grasp the benefit and limitations for this approach. We will delve deeper into the materials and chemical reactions used in the chemical hydrogen storage in subsequent solids to provide a comprehensive understanding of these methods. Liquid hydrogen tanks store hydrogen at near atmospheric pressure and require cryogenic materials such as stainless steels and aluminum alloy capable to withstanding the extreme temperature of minus 253 degrees centigrade. Solid state hydrogen storage. Solid state hydrogen storage is an emerging methods that involves materials such as metal organic framework and complex hydrides. These materials can absorb and release the hydrogen while remaining in a solid state. Solid state storage offers the potential for safe and efficient hydrogen storage, although it presents certain challenges. And those challenges we have to find out the solution of the challenges. And we people are here to find out the challenges for storing the solid state hydrogens. In solid state hydrogen options, hydrogen is stored either in the form of hydrides, that is metal hydrides, or complex hydrides, or chemical hydrides, or molecular hydrogen absorbs on the solid surfaces. And this hydrogen can be released whenever required by the thermal stimulations or any other techniques. Just I want to place the few slides like hydrogen storage as a compressed gases. The equation of the state is PV equal to nRT. These are the well known to all of you. The special gas cylinder for the hydrogen storage. Storing hydrogen gas in pressurized cylinder is the most technically and straightforward methods and most widely used for a small amount of the gases. So you can see that hydrogen storage in the carbons. These approach for the cuttings and titanium incorporations with the titanium oxide. So this is also helpful to have the storage of the hydrogen. You can see these nanotubes, which is shown over here, and you can store the hydrogen over there. If you can see the storage as a liquid, so you can have the different tanks or the cylinder where you can store as in the form of liquid. You can see this one table, hydrogen storage as a liquid. So if you see the diesel, if you want to store, or the gasoline or methane or methanol or the hydrogen, so in the compressed form for using the fuel for the car, the hydrogen can be stored as a more in amount compared to the diesel or the gasoline. So this way, really it is a very interesting area. Further enhance the storage capacity in the form of liquid, compressed liquid, or maybe the compressed gas or the solid state in the form of hydrates and all. So here you can see this. That is megajoule per kg. That means 120 megajoule kg, how much energy is stored over here. Here effective bundles delaminations. So these are the few. So one will be the physical methods, the compressed air, then cryogenic liquids and all. Another is storage as a hydrogen generating chemicals. And moreover, you are also knowing that water means we have the hydrogen and oxygen, H2O. And from there also you can heat it at a temperature of nearly 2500 degrees centigrade in a closed chamber. Then you will find it, the hydrogen will be separating out, but at a temperature of 2500 degrees centigrade. And again, release of this temperature is again a big task for all of us to find out some solution for this. Otherwise, it may be much cheaper compared to the other cases. So now we will talk about the advancement or innovations. What are the advancement has taken place to find out the way for the hydrogen storage. So this slide covers the recent advancement and innovations in the hydrogen storage materials and the techniques and the technologies. It focuses on the latest breakthrough, cutting edge research and pioneering solutions that are pushing the boundaries of hydrogen storage. The stringent technical targets set forth in hydrogen productions, hydrogen storage, hydrogen conversions, and so on. So these advancements in the hydrogen storage systems have been a focus of research and development due to their critical role in enabling the use of hydrogen as a clean energy carrier Some notable advancement includes nanomaterials and composites. As we have discussed in the beginning about the nanotubes, carbon nanotubes. So nanomaterials and its composites will have the key role, and it can work as a materials to store the hydrogens. The development of advancement nanomaterials like carbon nanotubes, metal organic framework has improved the absorption and desorption of hydrogen, increasing storage capacity and efficiencies. Then metal hydrates. So metal hydrates is also useful. That is, a research has led to the discovery of new metal hydrates with improved hydrogen storage properties. Some hydrates can operate under more moderate temperature and pressure conditions, making them more practical for various applications. Liquid organic hydrogen carriers, LOHCs, are chemical compounds that can store and release the hydrogen reversibly, and they offer a safer and more energy dense alternative to gaseous storage. Advances have been made in that developing more efficient LOHCs systems. Cryogenic storage. Cryogenic storage of liquid hydrogen has seen advancement in the materials and insulation techniques, which helps reduce energy losses due to boil off during storage. High pressure tank. Advances in material science and tank design have improved the safety and efficiency of high pressure hydrogen storage tank. Composite materials and advanced manufacturing process have made tanks lighter and more durable. So whenever we are manufacturing the composite materials tank, we should think about the weight. It should not be heavy in the weight. It should be in the light in weight, as well as having the durability. Then chemical hydrogen storage. Research continues on finding new chemical compounds for hydrogen storage, as well as catalysts and reactors that can make the release of hydrogen more efficient. Safety measures. Advances in safety systems, including leak detections, pressure relief mechanism, and material that can resist hydrogen embrittlement, have enhanced the overall safety of hydrogen storage and transport. Underground and above the ground storage. Improvement in the monitoring and maintenance of the underground storage facilities and the development of above ground storage solutions are enhancing the reliabilities and capacity of the hydrogen storage. So this is also one of the focused area where one can work. Hydrogen storage for transportations. Advancement in the hydrogen storage techniques are crucial for fuel cell vehicles. Innovations in the tank design and materials have made it possible to store more hydrogen in a compact and safe manner for use in the cars and the trucks. One more, that is, we have to have the, say we are receiving the solar energy and we are supplying to the grid. Similarly, feel it possible here also that we can have the correlation with the grid and the renewable energy integrations. Here also, we have the integration systems. So people are working on it. Hydrogen is increasingly seen as a way to store excess renewable energy for later use. So innovation in the large scale hydrogen storage, including underground, overground tanks, are helping integrate the renewables into the energy grid. So once it will be going to the grid, or it will, so from there, or you can, so similar way, we have to think of it and we have to plan on it. There are many challenges. This slide addresses the critical challenges in hydrogen storage. These includes cost effectiveness, safety concern, achieving high energy density. Really, this is the achieving high energy density is a big challenge, and ensuring the durability of storage materials and the systems. Understanding and addressing these challenges is fundamental to widespread adoptions of hydrogen as a clean energy solutions. By recognizing and discussing these hurdles, the presentation prepares the audience to appreciate the complexity of implementing the hydrogen storage systems and highlights the need for ongoing research and innovations. So really, you all are here. You have listened, these are the challenges we have to work out. We are the future engineers. We are the researchers, stakeholders. We can find out the solution and find out and take the challenges of address in these slides. Hydrates are poor thermal conductors with relatively high enthalpies of formations, and the absorption reactions is usually endothermic and absorption exothermics. This means that considerable amount of reaction heat needs to be dissipated during the hydrogen charging, and heating is needed for hydrogen absorptions. Now we'll see the future scopes. As we all are knowing, it's have the very bright futures, and it will give the comfort to a human life in the form of energy, source of energy. So in this section, we explore about the potential future development in the materials for hydrogen storage systems. It highlights the role of materials research in the shaping the trajectory of hydrogen storage technology. Anticipated advancement may include novel materials, improved performance, and increased safety. This slide engages the audience imaginations, emphasizes the importance of ongoing innovations and investment in the materials to realize the full potential of hydrogen as a clean energy carrier in the futures. Hydrogen is widely accepted as a possible energy carrier owing to its advantages such as ease of availability, renewability, and environmentally friendly in nature. So hydrogen storage is the liquid in the form of liquid or the gaseous, poses the safety and transportation challenges. In this context, metal hydrides are a vital solutions, and there are many other solutions which is lying on you all to find out. So it's have the future prospects. Now we'll see the applications of it. By illustrating these applications, audience gains the concrete understanding of the value of hydrogen storage materials is enabling clean and sustainable energy solutions. The examples provided here are the tangible evidence of the importance of the materials in a hydrogen-based economy. And definitely once you will, all the garis, cars, or the automobiles, or flight, or aeroplanes, or the many other, in the case of aerospace or military, or maybe the vehicles, if they will use this hydrogen as a fuel, definitely our economy will improve. So for the development of the nations, this is very, very important. Hydrogen absorption storage systems find various applications across the different industries. Due to hydrogen's versatility as a clean energy carrier. Here are the some key applications of the hydrogen storage systems. In the case of transportations, so that is nothing but the fuel cell vehicles, which is more popular nowadays, and people are focusing on it. So hydrogen is used as a fuel for fuel cell vehicles, where it is stored in high pressure tanks and converted into the electricity to power the vehicle's electric motors. And this fuel cell vehicles offers long driving range and fast refueling, and making them a potential solution for zero emissions transportations. Energy storage, like grid balancing. Hydrogen can be produced during the period of excess renewable energy generations, that is wind or the solar, and a store for later use. It can then be used to generate the electricity through the fuel cell when energy demand is high, and helping to balance the grid. Industrial process. So hydrogenations. Hydrogen is used in the various industrial processes such as refinery, petrochemicals productions. Hydrogen storage system ensure a reliable supply for hydrogen for these processes. In the area of aerospace, like rocket propulsions, hydrogen is used as a rocket fuel, and advanced storage systems are essential for storing the fuel as a spacecraft for missions to space. Recently, the Chandrayaan they have used. So there also you can use this as the source of energy. Then backup power. Emergency generators. Hydrogen fuel cell can provide backup power for critical infrastructures such as hospitals, data centers, ensuring the uninterrupted operations during the power outage. So there also it will be used as a backup power. Residential and commercial applications itself combine heat and power. Hydrogen can be used in CHP systems for residential and commercial buildings, providing both electricity and heat. A storage system helps ensure a continuous supply of hydrogen for these applications. Marine and shipping. In the area of marine and the shipping, hydrogen powered vessels, the hydrogen storage is used in ship and marine applications where hydrogen fuel cells are used for propulsions. Hydrogen refueling stations like petrol pump or the other source, other way. This is also can be one stations where the refueling can be done. That is hydrogen infrastructures. So storage systems are an integral part of the hydrogen refueling stations, ensuring the availability of the hydrogen for fuel cell vehicles. So as and when your vehicles are on the road and you feel that now it is about to over, then you have to go for the refueling of it, and that station has to be required. Chemical industries, hydrogenations of the chemicals. Hydrogen is a crucial reactant in various chemical processes, and storage systems are essential for supplying hydrogen to chemical manufacturing plants. Hydrogen mobilities. Hydrogen storage plays a role in developing the portable hydrogen fuel cells for applications like electric bike, a scooter, and drones. Space explorations, space missions, hydrogen storage systems are used in a spacecraft for storing liquid hydrogen, which is used as propellant for launch and interplanetary missions. So overall conclusion is we summarize the key points and take away from the presentations, and we reiterate the critical role of materials in hydrogen storage systems, their impact on efficiency, safety, and sustainability. We emphasize the importance of ongoing research and innovations in materials to address the challenges and unlock the full potential of hydrogen as a clean energy source. So I wish we have discussed the silent key features, applications, source of storage, the way of storage, and the materials which is used for the storing of hydrogen. And from here, I will request to the audience can take the silent features and the challenges, and that will helpful for the new generations or the societies or the industries who can develop the systems, and the storage of the hydrogen will be the important parameter or key area of research nowadays. So I wish everyone, hope you have understood some of the things and you will carry forward and you will take the challenges in the futures and you find out the solutions. So thank you, everyone.
Thank you, Professor Riser.
Yes, sir.
Thank you very much, sir. Thank you very much. I request all the participants to ask questions, whoever is interested in this topic, through messages or through direct. If you want to directly speak, I can unmute. Otherwise, you can type the message or put your thumb symbol.
I will appreciate if you can ask the questions. Yeah, audience, please.
Many of you are there here. Please ask the questions. Karthik KV. Thank you for delivering nice talk. Materials for hydrogen storage, improvising the efficiency. Thank you, sir. Thank you, Karthik. But we need questions from the audience. It is very useful session. Thank you, Suresh. Yes, I'm unmuting you. Ishrat Meera Mirzana. You can ask the question.
Good morning, sir.
Ma'am, a bit louder. Doctor, madam, bit louder.
Now, am I audible, sir?
Still louder, still louder.
Yeah, actually, I just wanted to ask few questions. First,
Madam, your voice is less. It is not audible clearly.
still it is not audible.
It's a little
slightly
better, but still
Okay.
slightly better.
Yeah, actually, for thermal decomposition, we are utilizing it, sir. Its capacity is 4,000 watt hours per kg. But is it safe, sir, to utilize for various applications?
That's why, madam, I said that at a high pressure, if you are storing it, sometimes it is very dangerous. So one has to work on it, on the particular specific materials which can withstand even the high pressure, so that it should not have the dangerous or unsafe for use.
Oh.
So there are a lot of challenges nowadays, and people has to work on it.
So, what are the suggested insulating material for storage tank, and so that the pressure can be maintained as per the application?
Insulating materials, madam, you please focus on the research papers. Presently, I am not remember which materials we can recommend.
Okay. Okay. And what exactly is the difference between composite cylinder and because carbon nanotubes are also CFRP, that's also like a composite person. What is the main difference between a composite cylinder and carbon nanotubes?
No, as and when you will make it as a composite, it will
Mhm.
it will be a light in the weight,
Yes,
and at the same times, it will give the sufficient strength so
true.
that it can withstand the high pressure.
Yes. So exactly like this, we can say carbon nanotube also as a composite cylinder only.
Yeah, it is in the form of cylinder only, but it is in the nano in size,
Okay,
and which have the higher amount of storage capacity.
okay, okay. So it's based upon the capacity, we are classifying it as a different. Is it, am
Yes,
I right, sir?
that is also required, madam.
Okay, okay, okay. Thank you, thank you, sir.
Madam, as sir said, carbon composite is also a composite material.
Yes,
That
true.
is what professor is telling.
Yeah, yeah,
Thank
I
you.
got that, but exactly, what is the difference in this? Yeah, I got the point. Thank you,
Yes. Thank you.
thank you.
Tatvam Joshi, sir, I have unmuted you. You can
Yes,
ask.
sir. Sir, I'm B mechanical student, third year student. And sir, in between you have shown the one book which has some chapters. So can you refer that book name?
Which one?
Sir, in between you have shown one book.
This is this one slide.
Yes, sir, this one. Is it a book
Ah.
or your slide you have made?
I have not made, it is made by someone else. For reference, I have brought it over here.
Okay, sir. Can you share it with sir? Or
Yeah, I will say to sir.
okay, sir. Thank you, sir.
Tatvam Joshi, all the materials the speakers will share with us. Then we can share to the participant. No problem about it.
Okay, sir. Thank you, sir. Lecture was very nice.
Thank you. Thank you so much.
One more,
So
one, sir,
thank you
one more
so much.
question. Sir, last question is there. Which type of
Yeah.
storage capacity is nearest for the practical use? Which storage capacity is currently used? Asked by the Ravi Verma sir in the chat box, sir.
In future, in the solid form, will be much effective one, will be better one. And but presently, we are using the carbon nanotubes for storage of the hydrogens.
Thank you, sir. Thank you.
Thank you, sir. Thank you, sir. Thank you for your kind, valuable time to spend with us and give a keynote speaker.
So I wish to thank my students and your colleagues who has
Thank you,
given
sir.
an opportunity to address this area, and really I am delighted to see you all. So can I make myself out? I have to move from here. Hello. Hello. Jiptesh. Jiptesh. Hello. Are you hearing me? लड़का लोग ठीक कर रहा है क्या? ओ अंदर नहीं गया ना? हाँ ठीक है वो भी anyway complete हो गया भैया. I was in so tense. वो ये जो है ना हमारा
Sorry, there is some internet issue here in the middle. Now, let me welcome the second speaker, Dr. Abhishek Paul. Anuhya madam, please introduce him. Please introduce our speaker.
Now, in the second session, we will explore Paul, Assistant Professor, Department of Mechanical Engineering, NIT Center. I'm delighted to introduce our guest, Dr. Abhishek Paul, sir. He has completed his PhD from NIT Agartala in 2018. He has published 23 journal articles, 7 conference proceedings with expertise in combustion, IC engine, fuel hybridization, alternative fuels, and energy systems, fuel synthesis. Currently, he is investigating a research project on development and testing of nano-doped hybridized biodiesel as pilot fuel for hydrogen dual fuel operation in a stationary CI engine. The project worth is 51.85 lakhs and is funded by DST, Government of India. We are eager to learn from your expertise, sir.
Thank you, ma'am. Am I audible?
Yes, sir.
Yeah. First of all, I'd like to thank Dr. Vishwanath Kumar, Dr. Jivitesh Kumar Panda, and Dr. Suravi Sharma for inviting me in this international short-time training program on recent advancements in fuel cell and hydrogen storage. It's indeed an honor for me to be a part amongst you and share some of my expertise. And just a second, let me share my presentation. I'm actually new to this Zoom platform, so
Welcome, sir.
yeah, thank you, Jivitesh. Thank you so much. Is it visible?
Yeah, sir. Visible, sir.
Which window am I seeing actually?
Yes, sir. Visible, sir. Visible.
Are you seeing this PPT presentation, this one?
Yes, sir. Yes, sir.
Or
Future of green hydrogen in the road transport.
you are seeing it in the presentation mode, I guess?
Yes, sir. It is in presentation mode, sir.
Okay, thank you. Thank you so much. So, good afternoon, everyone. I'm Dr. Abhishek Paul from Department of Mechanical Engineering, NIT Silchar. And today I'll be discussing on a topic, future of green hydrogen in road transport. Now, this is a overview of my presentation, and I'll start with the present energy scenario of the world. Presently, as we can see in this, in this first graph, that this shows the energy reserve that we have presently, that is fossil fuel reserves. And you can see that very soon, around 2051 around, we will lose our all oil reserves, petroleum reserves. And soon enough, we will lose our gas as well as coal reserves. So what will give us the necessary energy that we need for the development and keep the civilization going in its upward trend? Second graph shows our utilization of energy. Here we can see that as we are progressing along with our civilization, our energy demand is constantly increasing. And side by side, our fossil fuel reserves utilization is also increasing. And a very small part of this energy is being supplied by renewable energy sources. Coming back to the Indian scenario, here, this graph shows you an upward trend of fuel imports that we are doing to sustain our energy needs. And here you can see that day by day, our internal production is reducing. Now, this is only the one side of the coin. The other side of the coin is the environmental prospect. As we are utilizing more and more fossil fuel, we are also increasing the environmental pollution. And good thing that we have learned from our mistakes, and we have implemented different abatement techniques and different environment protection laws to reduce our environmental pollutions. And here we see that these laws in India are termed as BS laws, Bharat Standard Emission Norms, and BS1, BS2, BS3, and currently we're in BS6 norms. Here you can see that our these graphs particularly show only two types of emissions. that is particulate matters and NOx. And we see that gradually we need to reduce our emissions to keep our vehicles in an environment-friendly manner. Some more statistics. This is a statistic from United States greenhouse gas output, and you will see that around 29% of our total greenhouse gas emission. Greenhouse gases, as we all know, is gases like carbon dioxide, methane, and so on, which traps the solar heat and warms up our atmosphere. Around 29% of the total greenhouse gases are produced from transportation sector. Around 28% is produced from electricity generation, 22% from industry, 12% from commercial and residential users, and 9% from agriculture. So we see that majority of our greenhouse gas emissions are from the transportation sector, which is an alarming thing. Now, coming back to hydrogen, why we are so much thinking about hydrogen? Rather, before going to that, I should answer this one. Why we are so much eager about hydrogen? Because it has a lot of advantages. Some of them are summarized in here. That is, we can generate hydrogen from a diverse sources, which we will discuss in subsequent slides. The feeling of hydrogen in their storage is quite quicker as compared to battery charging. Obviously, battery charging takes a lot of time. It can be literally produced from any resources, and with a proper technology, we can produce it without any carbon footprint. If we can transport it over a long distance by pipelines or by transportation vehicles, it has a very high energy density. So we need not to carry very high amount of fuels in our vehicles to keep it running for long distances. It produces clean power. It's a clean power and fuel source. It doesn't produce much of an emission because it's a carbon or hydrocarbon deprived fuel. So it will not produce much of a pollution. It doesn't, during the production process also, it doesn't produce any industrial wastes, which can harm our environment as well. It is a versatile energy vector with a wide application, and safety concern regarding hydrogen utilization is similar to any natural gas or any gaseous fuel utilization. Now, after that, let us understand what is hydrogen. As we know, the word hydrogen came from Greek word hydro and gen, which stands for water generate. It was discovered in 1766 by Henry Cavendish, and later it was named by Anton Lavoisier. It is one of the most abundantly available material. In fact, 76% of the total atmosphere is, or universe is made of hydrogen only, and it is also the most abundant material in our planet. But why don't we see hydrogen in abundance in our atmosphere? Because majority of this hydrogen is actually in form of compounds that chemically combines with other materials to produce compounds. Hence, the energy content, so hydrogen content in our atmosphere is very, very, very less, almost 55.55 to 0.6 ppm only. And the total hydrogen in compound present in Earth is around 15.4%. Now, this hydrogen is present in three forms. That is protium, that is in its elemental form hydrogen, deuterium, which is the most commonly used hydrogen that we see, and tritium, that is three hydrogen molecules, atoms combining together. Now, this tritium is slightly radioactive, and it has its use in radioactive materials. The most common types of hydrogen, as we know, is the deuterium that we commonly refer to as H2. Now, there are a lot of processes of producing hydrogen. Some of them are summarized in here. Now, for the time being, I'm not going in details with it. The most common types in which we produce hydrogen is coal gasification or steam methane reformation. Another very promising process of producing hydrogen is the water splitting by electrolysis, which we will discuss in our subsequent slides. Now, according to the process by which the hydrogens are produced, they are color coded, and these color codes are given in here. These are green hydrogen, blue hydrogen, gray, turquoise, pink or purple hydrogen, yellow hydrogen, black, brown, white, orange, red, and there are some without color codes. Now, green hydrogen means hydrogen which are produced from renewable resources and through electrolysis process without releasing any greenhouse gas. So these are the cleanest form of hydrogen. Whereas blue hydrogen is produced from a mixture of natural gas and water heated at high temperature to produce steam reformation process. And in this process, whatever carbon dioxide is produced is actually absorbed or stored underground. Thus, this is a very low carbon hydrogen production process and produces almost no carbon dioxide. Gray hydrogen is the most commonly used hydrogen that we have right now. It is produced from steam reformation of natural gas and methane, and it produces sufficient amount of greenhouse gases like carbon dioxide and carbon monoxide. There are different variants of these gray hydrogen. These are black hydrogen and brown hydrogen, which are produced from coals, different grades of coals. Then we have turquoise hydrogen, which is comparatively a new type of hydrogen. This hydrogen is also produced from methane reformation or methane pyrolysis. Only thing is that its byproduct is a solid carbon, which we can easily remove from the production process as a byproduct. And it has different uses, like in car tires, in coating application, in plastic, in batteries. These byproduct carbon can be easily used. Then we have yellow, orange, and red hydrogen, which are produced from the electricity generated by solar, wind, and nuclear energy, respectively. Then, as I have said, we have black and brown hydrogen, which are produced from black, which is bituminous coal, and brown, which is lignite coal. Then we have purple or pink hydrogen, which are produced from electrolysis of water through direct application of nuclear energy. Now, there should be a caution with this type of hydrogen because they are radioactive. They may cause radioactive leakage if not handled properly. Then we have white hydrogen, which is the naturally occurring hydrogen. As I've said, naturally hydrogen do not occur in our planet. They are formed in they form compounds with different materials. So this natural white hydrogen is very rare. However, the byproducts of different industrial usage which produce hydrogen are also considered to be white hydrogen. And finally, we have some colorless hydrogen, which is the most recent type of hydrogen that we have produced. It is developed by a electromechanical device called artificial leaves, which integrate the solar irradiation with some catalyst to directly produce hydrogen by splitting water. And this obviously works as similar to the photosynthesis process. That's why it's called the artificial photosynthesis process. And still it's in its infancy, and scientists are still developing this technology. Now, let us have a look at the present scenario. Almost 44% of our total global hydrogen consumption is used in crude oil refining in hydrolysis processes. Around 37% is produced from ammonia production, around 12% in methane production, 5% in metal production, and only 2% in other processes. This 2% actually includes the vehicular uses, the road transport usage of hydrogen. On the production scenario, around 48% of total hydrogen that we use is produced from gas reformation of natural gases. Around 18% is from coal. Around 30% is from petroleum, oil, and around 4% from electricity, that is electrolysis. Now, this is a projection of global hydrogen demand predicted up to 2050. As we are developing our hydrogen-based vehicles, the requirement for hydrogen is increasing. Side by side, hydrogen is also being used for different other applications like power generation, industrial energy, building heat and power. And for these, the hydrogen demands are increasing significantly. With the best estimation we have, around 2050, our total hydrogen demand will be increased by tenfold, out of which around 154 million metric tons of hydrogen will be required in the transportation sector. Now, beneath this, we have a mileage sort of graph showing which technology can be used and how much mileage it can produce if used in a road transport. you see that this section represent the battery vehicles. This, excuse me. Okay. This is fuel cell vehicles, and this is bio or hydrogen powered vehicles. So we see that obviously hydrogen, among all these things, the battery powered vehicles, the fuel cell vehicles, and the direct hydrogen application vehicles, hydrogen vehicles have the largest largest mileage possible among all these things. As a result, there has been a significant amount of work done in developing hydrogen vehicles because their weight carrying capacity of hydrogen fuel cell of hydrogen fuel cell vehicles, if made in a large scale, like for buses, it is quite high. So we can utilize this fuel cell despite of their higher weight in road transport application. In United Kingdoms and in Germany, there are plans for utilizing hydrogen for fueling their trains, which will be a very cost-effective than electrification, and direct decarbonization will be possible with respect to the diesel power railways. And fuel cell vehicles are also expected to break even with the battery power vehicles in the next 5 or 6 years, around 2028. And it will break even in 2 or 3 more years with the conventional diesel vehicles. Now, some more interesting facts. If we run a hydrogen powered bus for 5 years, that is an AC transport bus, we will be able to remove around 11,34,000 pounds of carbon dioxide from the atmosphere. This carbon dioxide removal is equivalent to planting 13,189 plants, or taking out 108 vehicles for an entire year, or replacing 13,455 incandescent bulbs by LEDs. This is how much this hydrogen economy has to offer to us. But it has its own concerns also. From electric vehicles, that is the battery powered vehicle, we can attain an overall efficiency of around 70 to 90%. Compared to that, hydrogen has significantly lower overall efficiency, around 20 to 30%. But it is higher than that of what we are getting right now from internal combustion engine, which provides us around 15 to 19% of the efficiency only. So thus, the window is quite open for the research in the hydrogen application in road transport. Now let us focus our attention in green hydrogen. What is green hydrogen? The term green hydrogen means the hydrogen that is generated by renewable energy sources by most probably by electrolysis process without producing any greenhouse gases. That's why it is called green. Now, how it is produced? It is produced by splitting of water in electrolysis process in presence of some salt or some mineral. And so we all know that how electrolysis takes place. We have 2 electrodes immersed into the water connected to the power source. It produces the electricity that passes through this water, salted water, splits the water into hydrogen and oxygen. This hydrogen can be stored and utilized for different purposes, for fuel cells or for direct applications. Now, the problem is that how we are generating this electricity. If we are generating this electricity from clean resources, then we can call it a green hydrogen. And recent success in the energy technology and electric vehicles have shown us the potential of this clean energy network. And among all the resources, hydrogen has come up as one of the leading options for storing energy as compared to the conventional energy storages like battery, flywheels, compressed air, and so on. In the recently concluded UN climate conference in Glasgow 2021, that's COP26, governments over the world and industries have both acknowledged the importance of hydrogen as an important pillar for our net zero economy, net zero emissions also. And green hydrogen is the only type of hydrogen that can be produced in a climate neutral manner to reach the critical net zero emissions by 2050. And accordingly, India has also developed set its target to produce around 5 million tons of green hydrogen by 2030, that is the end of this decade, and also plans to add around more 175 gigawatts of green hydrogen-based energy sector in the upcoming years. Now, the green hydrogen can be produced from different processes, like utilizing the energy required from the different industrial waste heat generations, from nuclear energy, from renewable energy sources, etc. Most promising are these renewable energy sectors where solar, geothermal, biomass, wind, hydro, you name it, ocean thermal, tidal, all these energy sources can be utilized for producing the electrical energy, which can be further used for electrolysis process for producing hydrogen. Some other processes like photonic utilization of photonic energy for directly splitting water is also gaining much interest in the research domain, and a lot of work is being going on in this sector. Biomass to direct hydrogen generation through biochemical energy conversions are also gaining, like algae hydrogen generations, you might have heard about it, are gaining much interest, and we are doing a lot of research in this field for producing the biochemical hydrogen generation processes. But there are different challenges that are related to this green hydrogen generation processes, like it's summed up as 4E challenges. That is electrolyzer, energy source, end use, and endogenous resources. Electrolyzers are the devices in which we produce green hydrogen by electrolysis process. And as per 2021, the global manufacturing capacity of these electrolyzers are only 8 gigawatts per year. At present, India needs around 60 to 100 gigawatts of electrolyzer capacity, which is almost 12 times that of the total global production capacity. So we have a long way to go. Second is the energy resource. What kind of energy we need to use for this electrolysis process? As per the current estimates, an efficient electrolyzer requires 39 kilowatt hours of electricity to produce only 1 kg of hydrogen. So you can see that how much energy we need to spend to produce only 1 kg of hydrogen. So we need to improve the quality of our electrolysis process. Secondly, as green hydrogen requires renewable sources, so we need to produce our electricity for this electrolysis process from green sources. As far as India is concerned, we have only achieved around 119 gigawatt of 175 gigawatt targeted capacity by using solar, wind, biopower, and small hydro projects. So we have a long way to go to gain and surpass this targeted value of 175 kilowatts. Then comes the end use applications. Currently, most of our hydrogens come from chemical industry to produce ammonia for the fertilizer sector. Fertilizer production and desulfurization of fuels in petroleum sector. These hydrogen can be used as a heat source for industry as well as steel, cement, aluminum production, and so on. In the transportation sector also, it can be used as a fuel for heavy-duty vehicles in aviation and shipping industries. Hence, the conversion efficiency from one form to another carries a end use application. In the end use application will determine the scale of green hydrogen production applicability. That is how much we can how much we can utilize this green energy for our advantage in an environmental friendly manner will obviously dictate how we will develop our green hydrogen production technologies. And finally, endogenous resources. The one most important requirement for green hydrogen production is water, because we need water to electrolyze to produce hydrogen. And requirement of approximately 50 million liters of demineralized water is required for producing our electrolysis requirement. In a country of like India, where several states are already suffering for severe water shortages, this requirement of high amount of water is a very contradictory, puts us into a very contradictory situation, because whether we will use our water for our drinking purpose or for energy production purpose, that's a matter of debate. However, in this scenario, desalination can be a good solution, or desalination of our seawater and utilizing it for this electrolysis process could be a solution. However, there are problems. This will increase our physical footprint for desalination plants. Excess utilization of seawater will obviously affect our biodiversity, and it will create challenges and limitations in location of these electrolyzing units closer to the shore, sea shores. So we will not be able to, may not be able to properly utilize them in places where this sea, access to the seas are not that much available. Now, here is India's green hydrogen roadmap. Here we can see that around policy interventions causes around 4% utilization of increase in hydrogen energy share by 2030 in India, and around a $100 million US dollar investment is required for this purpose. Accordingly,
Excuse me, Dr. Abhishek, sir.
yep.
I think some participants are texting the messages that the PPT is not in a presentation mode. They're saying the text is too small.
Okay, that's what I was asking, whether it is in presentation mode or not in the beginning. So let me check it. What am I presenting? This one? I should be presenting this one. Now, can you see it properly?
Yes, now it is better, sir.
Yes, sir. Now it is clear, sir.
Much
Yeah,
better.
thank you so much. Thank you for
Sorry, I thought Jivitesh must have told you. Sorry about it.
it's okay,
Very good, sir. Thanks.
Thank you. Now, India has proposed some demonstration projects like Hydrogen Bharat trucking project that will run in the Delhi-Mumbai corridor. There are some port and logistics clusters which are being developed based on hydrogen utilization. There are industrial clusters that are being developed which will use hydrogen in steel and fertilizer factories. There are initiatives that are taking for utilization of municipal waste into biogas, and from biogas to hydrogen production process. There are development of coal gasification processes for hydrogen generation, but all these things will not cater to our green hydrogen initiatives. For the green hydrogen initiatives, Union Cabinet has set up some goals around 5 million metric tons of green hydrogen of annual production is to be produced, and for that around 60 to 100 gigawatts of electrolyzer capacity is required, for which around 125 gigawatt electricity needs to be generated for renewable sources. And for all these, government has offered around 19,744 crores of fund for these green hydrogen projects. These projects not only will provide us around 6 lakhs job opportunities, around 50 million metric ton abatement of carbon dioxide emission, but also will provide us a savings of around 1 lakh crore of import duties, and around 8 lakh crore of investment is also expected from these. Now, this is a projection of the budgetary allocation of Indian government in hydrogen production purpose, and you can see that gradually we are increasing our investment in hydrogen generation sector. This graph shows us the projection of at the pump hydrogen cost across Mumbai, Ahmedabad, and Delhi. Around 2030, it will be around somewhere around $6 to $6.2 per kg, which is equivalent to around 400 rupees per kg of Indian currency. That is for blue hydrogen. For the green hydrogen, the cost is quite high, around $9 and 600 rupees per kg. Out of which you can see that majority is for the production cost. Majority of this cost is due to the production cost of hydrogen, which is supposed to decrease with the advancement of technology and better production processes. And around 2050, we can expect a blue hydrogen pump cost around $5, and that is around 300 rupees, somewhere close to 300 rupees. But still, it is quite high as compared to our conventional petroleum-based fuels. So a long way to go for implementing this hydrogen-based economy. Now let us venture into the utilization, the fuel cell. As we know, fuel cell vehicles utilizes fuel cell, which utilizes the hydrogen and oxygen to produce electricity, which can be used uh, in a electric motor to produce the power. Additionally, these fuel cell vehicles also have high output batteries, which use regenerative braking for additional power production, and that can be provided to supplement the power to the electric motors. The one most important thing is that this large cylinder that this vehicle needs to carry. Now, this cylinder is definitely a problem for us. And as I've seen in the previous presentation by Dr. Ramnaresh Roy, a lot of research is being going on in storing of hydrogen in solid fuel cells and so on, so that the storage requirement can be reduced. Now, there are a lot of benefits and challenges in implementing these fuel cell vehicles. Benefits like it produces less greenhouse gases because it doesn't emit any emissions. It reduces our dependence on fuel. It produces less pollutants. It is quick to refuel as compared to any electric vehicle, any battery-powered vehicle, and it has a longer driving range. But the challenges are also quite large. That is, the cost of the vehicle is quite high as compared to any conventional vehicle that we have, engine powered. The cost of these vehicles are quite high. Second problem is getting the hydrogen to the consumer. Frankly speaking, not only our country, but all over the world also, the hydrogen dispensation systems are not that much popular yet. And this is a major hindrance in utilizing hydrogen for power generation sector, particularly for transportation sector. So until and unless we have a dedicated channel for supplying this hydrogen to the end user, any hydrogen fuel vehicle or hydrogen powered engine vehicle will not be that much successful. Third problem is the durability of the fuel cells. The fuel cells are still in research stage, although there has been a lot of implementation, but those have shown a lot of vulnerability. The cases of fuel cell blasting inside the vehicle are also being witnessed in many countries. Their deterioration at high temperature, their longevity has been into question for a long period of time now. And solving these problems requires a lot of research, which are being done as we speak. Another point is public education and acceptance of the people. People are quite accustomed to getting to use a normal petroleum fuel based vehicle. So shifting from a petroleum based vehicle to a fuel cell vehicle, which will produce less emission but will cost a lot, requires a significant amount of jump in our consciousness. We need to go beyond our thinking of utilizing these fossil fuel vehicles. And that has been a major challenge. Acceptability has been a major challenge in this any kind of alternative fuel vehicles. These are two case studies or two which are done by Toyota and Hyundai. This is Toyota Mirai launched in 2022 and Hyundai Nexo Blue also launched in 2022. Here you can see that the mileage is around 72 for the combinations of city and highways, 74 for city and 70 for highways for the Toyota Mirai. And Hyundai Nexo is also have similar 56 to 60 miles per kg of fuel economy. The range is around 380 to 402 miles. Both of them are compact SUVs, which uses lithium-ion batteries. One has a 311 volt and then one has a 240 volts of lithium-ion battery. But these are available only in US. That too for a very small numbers. These are basically demonstration projects. These type of technologies needs to be developed so that more and more fuel cells vehicles can be introduced into our market, so that only when they will be available, only then people will think about taking them. Next part is rather direct application of hydrogen in automobile vehicles, in automobiles. Utilizing hydrogen through fuel cell requires a fundamental change in the structure of the vehicle. You need to take out the engine, you need to install motors, electrical motors, and the entire structure of the vehicle thus changes. You need to entirely design the automobile for that. Its powertrains, its braking, its regeneration systems, everything needs to be recalculated and recalibrated. However, there is a simpler way of utilizing hydrogen by slightly modifying our conventional engines. Now, this hydrogen can be utilized both in CI engine and in SI engine. In CI engine, actually, we have seen some application of hydrogen also. That is in Delhi, we have some CI engine vehicles, CI engine buses, which are running on hydrogen. Of course, these are demonstrative projects, but these demonstrative projects eventually pave the way for large-scale deployment of these type of vehicles. Now, what are the improvements that we can have by utilizing hydrogen in this CI and SI engines? We can have a higher engine performance. Now, particularly in terms of the efficiency, energy utilization, hydrogen is very good. Hydrogen has a calorific value, that is heating value of around 151 kilojoule per kg. Compared to that, petrol has a heating value of around 42 megajoule per kg. Diesel has somewhere around 43 to 44 megajoule per kg. So we can see that the heat content of hydrogen is almost 3 times that of our conventional petroleum vehicles. So the energy requirement is 3 times lesser if we utilize hydrogen directly in our vehicle. This gives us a better economy, and we can produce same amount of power by burning less amount of fuel. Thus, our thermal efficiency is increased and our power production remains the same. The exhaust emission is another aspect of utilizing hydrogen directly into in our engines. Hydrogen is a hydrocarbon neutral fuel. It doesn't have any hydrocarbon. So whenever we are burning hydrogen, what we are producing as a product is water only. This water can again be utilized for hydrogen generation. And most important thing is that we are not producing any kind of hydrocarbon. We are not producing any kind of oxides of carbon. We are not producing any kind of particulate matters. So as a result, our entire emission spectrum becomes more or less clean. Of course, there are problems. Hydrogen generation, hydrogen combustion produces very high temperature because of its high heat content, and thus it produces high amount of oxides of nitrogen. But that also can be controlled by advanced combustion strategies and controlling the combustion processes. Now, for utilizing this hydrogen into our engine, very small modifications are required. Like we need to modify our operating conditions, how we gonna inject our fuels, how we're gonna store our fuels, and how we're gonna control our combustion process. All these things needs to be controlled. For example, if you are using petrol in a SI engine, you need a carburetor or a fuel injection system to supply the fuel into the engine. If you use hydrogen, we don't need any carburetor because you can simply release the hydrogen into the intake manifold and it will make a fuel mixture, homogeneous air fuel mixture. Then this homogeneous air fuel mixture can be supplied to our combustion chamber and we can have combustion. So the complexity of the fuel delivery system can be much reduced in case of hydrogen application in a CI engine. Another thing is that modification of the ignition system. Now, hydrogen is a very flammable gas, as we know. So ignition system needs to be modified accordingly so that it can ignite our hydrogen air mixture an appropriate time to get the maximum power out of our air fuel mixture. Then the positioning, this includes the positioning of our spark plugs, and its timing needs to be controlled, because the same timing which are used for petrol application cannot be done for hydrogen application because hydrogen is having a higher octane number. This means it has higher autoignition temperature. So its ignition needs to be done at an appropriate time where we can have proper power development near our top dead center to get the maximum power output and better thermal efficiency. In case of CI engine application, hydrogen may be thought about to be a kind of an offbeat fuel because hydrogen has high octane number. It is a very low cetane number. So obviously, one may think that CI engine application, hydrogen is not meant for CI engine application, but there are a lot of work that has been done on utilizing CI engine hydrogen in CI engine application where hydrogen hydrogen is used as a primary fuel and diesel is used as its ignition source. Now, there are some applications of hydrogen in direct automobile application is shown in here. We can supply our hydrogen through our port fuel injection or we can directly inject in our combustion chamber. Ignition of these hydrogen can be done a different way. We can have a homogeneous charge compression ignition where hydrogen can be compressed with some other high cetane fuel to ignite the charge and to have combustion. We can use a spark ignition method and we can use some pilot diesel as ignition source for igniting our hydrogen. Then in direct injection also we can use the same principles of glow plug or spark ignition on the pilot fuel. So how does hydrogen can be used in CI engine application? That application of hydrogen in diesel engine. Due to its high octane number and very low cetane number, hydrogen cannot be combusted or ignited by compression alone. So direct application or standalone application of hydrogen in CI engine is not possible. In fact, there has been a lot of experimentation for direct application of hydrogen. The compression, we know that how to increase the in-cylinder temperature inside the combustion chamber. Now, the in-cylinder temperature is responsible for igniting the fuel in a diesel engine. It is the in-cylinder temperature that elevates the diesel air mixture to its auto-ignition temperature, which eventually ignites all by itself spontaneously. One way of increasing this in-cylinder temperature is by increasing the compression ratio. As the compression ratio increases, the in-cylinder temperature and pressure increases, thus producing more combustible condition. But it has been tested that with a compression ratio of as high as 45, hydrogen could not be ignited. That means the temperature that is generated with a compression ratio of 45 is not sufficient to reach the auto-ignition temperature of hydrogen. So it is not possible to directly use hydrogen in a standalone application of hydrogen in a CI engine. Rather, what we can do is that we can use hydrogen as our primary energy supplier, and we can supply it through our intake manifold. And we can use a secondary diesel injector. These diesel will act as the high cetane, low auto-ignition temperature ignition source. So whenever the compression heat will be generated, the diesel will ignite, and this combustion of diesel, small amount of diesel which is being combusted inside the combustion chamber, will produce the necessary heat and the flame for igniting the hydrogen. Then once the hydrogen is being ignited, it can combust inside the combustion chamber, producing high amount of charge. Now since high amount of pressure, now since hydrogen has a very high heat content, so we can produce the same amount of heat or work from the engine by burning very less amount of almost 1/3 of the total requirement of fuel if we utilize hydrogen. However, there are problems, as I've mentioned, with hydrogen combustion under this is called dual fuel method. That is where diesel and hydrogen can be simultaneously used. Hydrogen acts as the primary energy source and diesel acts as the pilot fuel or the igniter fuel. But there are problems with this type of combustion also. One of them is small utilization envelope of hydrogen. In this process, since the combustion kinematics and the combustion dynamics are not controlled, we cannot ensure that entirety of the hydrogen will be utilized or not. As a result, the hydrogen utilization increases side by side, we cannot increase the quantity of hydrogen that we can use in our dual fuel engines to infinite levels. That is, we cannot go beyond, let's say, 30% of total energy through hydrogen, because after that the combustion starts to degrade and we cannot increase the participation anymore. Degradation is primarily due to the loss of control over the combustion problem. Now, this control can be attained by carefully monitoring the flow rate of the hydrogen and the diesel inside the combustion chamber. In dual fuel mode, that is one of the problems, because we do not control the fuel flow rates sufficiently to control the combustion. However, if we control the flow rates properly, then we can attain a control over the combustion dynamics. How? Because in that case, the concept of RCCI comes into action. RCCI means reactivity control, compression, ignition, which is also one of my fields of research. Here, what we do is we introduce hydrogen into our combustion chamber, which has a very high auto ignition temperature. So whenever the temperature will reach to its auto ignition point, only then it will react with the air and produce the combustion. So that's why it's called a low reactive fuel. Whereas diesel has a low auto ignition temperature and it can attain its auto ignition temperature quickly and easily react with oxygen to produce combustion. That's why it's called high reactive fuel. So by controlling the quantity of low reactive fuel and high reactive fuel, we can precisely point where we want to start our combustion. At any point of time, by controlling the fuel flow rates of both diesel and hydrogen, we can pinpoint where we need to start our combustion. Thus, we can have a better control of our combustion process, and this gives us a better emission spectrum and higher power production spectrum also. For example, a dual fuel engine never goes beyond efficiency of, let's say, 30%. But with a RCCI diesel hydrogen RCCI engine, we can reach efficiency as up to 60 and 70%, which is not at all possible in any kind of CI engine application. Additionally, since we supply a very small amount of hydrogen because of its high energy content, the combustion takes place at a lower temperature inside the combustion chamber. As a result, the formation of NOx, which is one of the most potent emissions from hydrogen combustion, can be reduced by controlling the combustion kinematics. As a result, we get both sides of the coin, best of the performance and best of the emission as well. And this is the direct application that I have discussed with that. With direct hydrogen application, we can have a 80% reduction in direct particulate matter, around 22% reduction in NOx emission, around 25% reduction in CO, and around 8% reduction in CO2 emissions. With that, we can have around 7 to 14% of fuel saving and 10% increase in torque by utilizing hydrogen in our conventional diesel unit with small modifications. So the benefits, as we all can understand now, are almost zero emissions, longer driving range because of the higher energy content, quick refueling because hydrogen can be refilled quite quickly as compared to any electric vehicle or any fuel cell vehicles. And it has a higher compatibility than existing infrastructure. You just need to modify very small amount of the engine infrastructure to introduce hydrogen directly into it. You just need a separate hydrogen injection system comprising of a cylinder, a regulator, a pressure reduction valve, a flame arrestor, and a flow controller. That's it. And an injector. And you can install this injector into your intake manifold, and you can directly convert your CI engine into a hydrogen engine directly, or for that matter, SI engine into a hydrogen engine directly. However, due to the higher cost of production till date, these technologies have a lot of challenges for commercialization. Again, refueling infrastructure comes into action. We don't have sufficient refueling infrastructure. In fact, I would like to share one experience, my personal experience. I'm staying in Silchar, Assam. And for my research, whenever I need to get hydrogen, I have to wait for around 1.5 months because this hydrogen is refilled. My hydrogen cylinders are refilled in Gujarat and brought back to Silchar where I get my cylinders. So it takes around 1.5 months to get my cylinders filled. So infrastructure development, if I could have got this hydrogen closer to Silchar or even in Guwahati, I could have done some more work with less amount of time being wasted. Third is the energy efficiency. Energy efficiency all depends on how you utilize the hydrogen. If you have good control over your hydrogen and fuel rates, you can have higher efficiencies that like that we have achieved in our RCCI operation. We have around 62% of efficiency achieved in my own lab, and some other researchers have gone on to achieving 70 to 80% efficiencies also in direct combustion of hydrogen in CI. So the advantages are also there, and there are some disadvantages, but this is all food that we need for carrying out our research to make hydrogen vehicles more acceptable and more affordable to normal people. So the potential solutions for direct application of hydrogen obviously is technology development, which we the researchers are doing, and very soon I think we will have our first demonstration project in road with hydrogen powered vehicles, hydrogen powered CI engine vehicles. Government also needs to take a lot of incentives to promote this hydrogen economy in our automobile sectors, and collaboration among different stakeholders like researchers like you and industries needs to collaborate to bring this technology in the market so that general people can have a taste of it. And the future aspects, obviously expansion of the refueling structure is very much necessary. We need to increase our investment on hydrogen research and its implementation, and a wider adaptation in commercial vehicle is of topmost priority. So with this, I conclude my presentation with a single line that hydrogen is a clean energy source and advantageous for the automobile. If we utilize our hydrogen properly, and we develop our technologies for cleaner hydrogen production, this could be the fuel of the future. Thank you. This is all. This is Dr. Abhishek Paul concluding my presentation. And if you have any queries or any questions for me, I can be reached at this email. And with that, I conclude my presentation, and thank you.
Thank you, sir. Thank you very much.
Thank you. Thank you.
It's been a very wonderful presentation, sir. You have dwelled very much into details.
Thank you, sir.
Thank you, sir. Sir, I will add one line regarding about Abhishek, sir. Actually, when we are in NIT Agartala, means whatever we learn in the IC engine, so mostly we learn from him only. Kind of, we can say,
not like that.
no, this is true only, sir. Actually, we are, means, probably I'm saying we are talking about like men of ethanol. So this is the tag we given Abhishek, sir. Because the reason, even if now if you search in Elsevier, most of the paper related to the ethanol before 3 years back or 4 years back, it belongs to SAR only.
Excellent, excellent.
Now I have shifted to hydrogen.
Yes, sir. Yes, sir. But anyway, sir, like new technology, like trade-off analysis, whatever we now also we are doing, that is from Abhishek sir only, and kind of or maximum optimization technique. Sir make us learn, and kind of very good figure. Now you seen also in the PPT, so figures are there. Same thing also if you see in the paper, like how deep lot uses, how origin uses, will maximum we learn from him only. So it is a proud moment for me that today he is our guest only. Thank you, sir. Thank you for giving the valuable time to us.
Thank you so much.
So I requested to the participants, if you have any query, kindly raise your hand and you can put the question in the chat box. Please.
Everyone, please ask the speaker the questions. We encourage you to ask the questions.
Yeah, Tom Joshi, sir. Please, you can ask the question.
Yes, sir. Sir, as you have tell us that we are using hydrogen and diesel engine, diesel in engine. So, sir, there might be chances of reaction of hydrogen with diesel. So, how we can prevent them, or what are the reactions that could happen?
Actually, we are working. We need hydrogen to react with hydrogen with diesel inside the combustion chamber, that is how it burns. What happens inside the combustion chamber, it takes place in a very small period of time. So it doesn't get any chance to react with diesel. Rather, the reactions that take place between hydrogen and diesel inside the combustion chamber is all combustion. And we actually need this reaction to take place so that we can utilize all the energy from hydrogen as well as from the diesel in our power production applications.
I am unmuting you, Shankar Das, sir.
Yes, sir.
Yes,
Shankar sir, please ask.
Sir, thank you very much for nice presentation. Are you hearing me, sir?
Yeah, I can hear you. Please carry on.
Hello?
Yeah, please carry on.
I was also an NIT Agartala PhD student. Now I am in Gangtok, Sikkim, sir, Central University.
Which year?
Sir, really presentation was good, but I don't
Sir,
have that
he
much
is
of knowledge
in
the
my batch
hydrogen
only,
field, but can I ask?
Okay.
He did his work under Prasun sir.
Okay,
And now
okay.
he's working in Central
Oh,
University Agriculture.
yes. I remember, Shankar.
Yes, sir. Yes, sir.
Yeah. How are you, Shankar?
So, sir, I'm fine, sir. How are you, sir? After many days,
I'm
I'm
good.
looking
Yes,
at
yes. Yes, I'm good.
Shankar sir, can you switch on your camera also? You can switch on your camera.
Yes, sir.
If it is possible.
Definitely. I can.
Yeah.
Okay, definitely. Yes. Can you see, sir? Okay.
No, it's not visual. Okay, sir, you can continue.
No, I think no, camera they cannot switch on, sir. It is in the background settings they have switched off.
Okay, no issue, sir. Then, sir, you
Okay.
can ask the question, sir, please.
Sir, actually, what I'm asking, the fuel cell, the hydrogen, see, many lectures I have listened from the beginning, all are very interesting. Thing is that the domestic purpose, like inverter, battery, can it be made by this type of fuel cell, sir?
Theoretically, yes, but it will not be economical at all. What is a fuel
It
cell?
will not be economical.
Obviously, with the present technology, it's not at all economical. What is a fuel cell? Fuel cell is just a cell where you supply hydrogen and it interacts with oxygen to produce the electricity, and that electricity you can supply to your inverter.
Okay,
But storing hydrogen and getting those technologies in your household is still not economical. But theoretically, yes, it's possible.
Muthukumar, sir.
Yes, sir. Yes, sir.
Hello.
Sir.
Hello.
Yes,
sir,
sir.
good afternoon.
Hello.
Sir. I am Dr. Muthukumar.
Yes, Dr.
Hello.
Okay, sir.
Am I
Hello.
audible?
Yes, sir. You're audible.
Hello. Yes, sir.
Yes.
Sir, I have a question, sir.
Yeah.
Sir, can we directly use the hydrogen in IC engine, sir?
Sorry.
As a fuel, as a hydrogen, can we use this hydrogen as fuel directly in IC engine, sir?
Yes. We can directly use hydrogen in IC engine, both in spark ignition as well as compression ignition engines. In spark ignition,
What about the efficiency, sir?
sorry.
Efficiency of this hydrogen fuel compared to petrol or diesel, sir?
Efficiency. I'll just give you an example.
Yeah.
I'll just give you a practical example.
Yes, sir.
Hydrogen utilization in CI engine. Okay. So when you
Yes, sir.
utilize diesel in your engines, how much maximum efficiency you can attain? 30%, let's say.
30, yes, sir. Around 30
Around
to 40
30.
maximum.
Whenever
Yes, sir.
whenever you use hydrogen in your CI engines, in
Yes, sir.
combination with diesel, because you need diesel also to ignite that hydrogen. Okay, it will not ignite by itself. So you need diesel, some amount of igniter fuel. So whenever you are using diesel and hydrogen under dual fuel mode, you can have efficiency in the range of 25. Okay, it's not good for us.
Oh,
Why we are reducing?
Okay.
Because we cannot control the combustion kinematics. But if we can control the combustion kinematics by precisely controlling the energy that you are putting inside in form of hydrogen as well as in form of diesel, you can actually control the combustion, and controlling the combustion will give us better utilization of fuel energy. And in that respect, in my own lab, we have attained efficiencies up to 62%. Can you imagine getting
62, yes, sir.
62%
No, sir. No, sir.
from a CI engine?
Yeah.
First, in our initial run, we thought we have made some mistake. Then we have changed the entire system. We have calibrated everything. We have bought the engine manufacturer here to calibrate everything. In
Yes.
front of them, we have run the system, and again, we have received closer to 62% efficiency. That is because we
Sir,
were.
have you modified any? Sir, please, you proceed.
Yeah, that is why, because we were running we are controlling the reaction kinematics through RCCI mode of operation. Yes, we have made certain modifications to our engine structure. We have recalibrated our ECUs. We have programmed our ECUs to precisely control the combustion kinematics. And there are some small modifications that we have made in our fuel flow systems. Better control we have attained with our fuel flow system, so that we can precisely control the fuel flow inside the combustion chamber, so that we can control the combustion kinematics.
Yes, sir. So in which ratio you are mixing hydrogen and diesel, sir?
We are not
Ratio of mixing.
we have.
You said you are mixing diesel with the hydrogen.
It is actually not mixing. The diesel and hydrogen are supplied in two different lines. They are mixing inside the combustion chamber. The ratios in terms of energy, we have gone up to 80% utilization of hydrogen energy. That is,
Okay.
total energy, whatever we have, 80% of that is, sorry, not 80, 70% we have. 70% of the total energy is supplied by hydrogen, and only 30% is supplied by the diesel. That is the maximum could attain in our labs.
Yes, yes. So you achieved a 62% efficiency.
Efficiency with 40% hydrogen utilization.
Okay. Oh, in different ratios you are getting. Okay,
yeah,
sir,
obviously
okay.
at different ratios,
Okay,
we
sir.
have found that the optimal utilization of hydrogen for diesel operation is 40%. And in our other study, we have modified our biodiesel with some nanoparticles and some catalyst, and we could increase this envelope up to 50% also.
Okay, sir. Okay, sir. Sir, one more doubt, sir. Can we use hydrogen only as a fuel, sir?
In CI engine, we cannot, but in SI engine, we can.
We can. Okay,
Yeah.
okay. What about the efficiency if we use in that petrol engine?
We will get better efficiencies and better fuel economy also, because of the higher calorific value of the hydrogen and clean burning characteristics of the hydrogen. But some more modification to the engine, like as I mentioned in my presentation, is required.
Okay, sir. Okay, sir.
Let's now.
Is it used by any commercial? Is it used?
Sorry?
One more word, sir.
Yeah.
Is it used commercially at anywhere, sir? This hydrogen as a fuel on-road vehicles, is it used, sir, in India?
Yeah, there is a demonstration project running in. There is a bus running in Delhi, which is using hydrogen as fuel. It's a demonstration project. Outside India, there are also a lot of buses running on hydrogen, but most of them are running on fuel cell technology. Direct application is not that much.
Okay, sir. Okay, sir. Thank you, sir.
Thank you. Thank you so
Thank
much.
you.
Thank you.
Let's now give a chance to Gopi Krishna, sir. I'm unmuting you, sir. You can ask the question. Gopi Krishna.
Excuse me, I will have some water.
Yeah. I think
He kept one question actually.
yeah, it is in the chat box.
I want to know your thoughts on this. At high temperature, hydrogen reaches with nitrogen in the air to form NOx emission.
Yeah.
Even though the hydrogen produces green, can we call the IC engine as a green process?
Yes, hydrogen burning engines can be called green if we control your combustion dynamics. In dual fuel mode, as I mentioned, NOx emission is one of the most prominent emissions from the engine. It's actually the only emission from the hydrogen engine. Hydrogen doesn't produce carbon dioxide. It doesn't produce carbon dioxide. It doesn't produce any hydrogen. Only prominent emission is the NOx, because of the high temperature that it creates. And why this high temperature is being created? Because uncontrolled hydrogen combustion inside the combustion chamber produces very high temperature that produces high NOx emissions. Now, if we can bring the temperature inside the combustion chamber low, then we can reduce the NOx emissions also. So with a precise control, that is with RCCI control, we are able to go very lean in hydrogen utilization in our engines, and thus we can produce a low temperature combustion which can reduce the NOx emissions. So we can simultaneously produce higher efficiencies and low NOx emissions with hydrogen utilization using the RCCI mode of operation.
Okay. Navya,
One more question. Yeah.
I have
Madam
unmuted
asked-
her.
Yeah,
No,
please.
Navya, madam.
We can take a number of questions because he is the man of ice engine. So we can ask. It's a very better opportunity for us.
Yeah, I think
We
she's
can
asking.
ask.
Yes, I'm always open for your questions.
Yeah,
Good
thank you,
morning,
thank you,
sir.
sir. Yeah.
Good afternoon. Good afternoon.
Sir, you have told that you have improved the combustion characteristics by controlling certain parameters,
Yeah.
like fuel injection strategies and fuel injection timing strategies and fuel injection mode, everything. Sir, have you also modified the piston ball geometry in order to attain the better combustion?
Yes, yes,
and also to
actually-
improve the.
Yes, that is one of the research that presently going on in my lab. One of my PhD scholars is actually working on piston bowl geometry for efficient utilization in RCCI mode. Actually, we have found that there is the conventional pistons that we use. Although they give good response in RCCI control, but there is a particular shape in which my students are working on, which gives us far better efficiency and far better control over the combustion. And unfortunately, I don't have the material right with me. But yes, hydrogen engines can be benefited with piston bowl geometry by altering the piston bowl geometry. Yes, it is possible.
Okay. Sir, also due to high temperatures in the combustion process, because of the addition of hydrogen, it enhances the combustion temperature. Also, NOx is produced, as already you told. Can it be controlled by other methods like
yeah, it
other
can be
methods, sir?
controlled by other methods like EGR, recirculation, or by methods like water immersion.
Catalytic converters.
Yes, catalytic converter also. But I am a little bit against these methods because they tend to degrade the combustion. Like if you go for EGR, it will reduce the oxygen content inside the combustion chamber. So it will reduce my combustibility and thus it will reduce the emissions, which is
Yes,
a
sir.
negative approach. So I am against this negative approach of reducing the emissions. So that's why I'm not using any kind of EGR or water emission or any other technologies, urea catalytic converter, so that matter. I'm not using anything. I am trying to directly control the combustion kinetics so that emission can be reduced without hampering the combustion.
Okay. Okay, sir. Thank you, sir.
Yeah, thank you.
I think there are a lot of questions for this session, maybe.
Yeah, we will
This
take the last
Last
question.
time we are hearing many questions from last 3 days.
So
Yeah.
this will be the last question, sir.
Yeah.
Definitely.
Lakshmi,
Rest of your participants can send me your questions in my mail and I'll definitely answer them.
so nice
Yes.
of you, sir. So kind of you. Lakshmi, madam, you can ask. I have unmuted. Okay, I think we can read from the chat box. What measures are in the place to ensure that production of green hydrogen remains sustainable with minimal environmental impact?
Sustainability, we need to develop technologies. We need to develop better electrolyzers, efficient electrolyzers. We need to increase research on hydrogen electrolysis process. Catalytic electrolysis is one field that is very promising, and one of my friends is working on this electrocatalytic hydrolysis of water for hydrogen production. She's working in Simri Durgapur. That's a very prospecting work. I must appreciate that. And for hydrogen production, additionally, we need to work on our renewable energy sources for electricity generation, because the electricity that we are presently using are still fossil fuel based, and we can never achieve green hydrogen if we are utilizing fossil fuel for generating electricity. So we definitely need to concentrate on producing our electricity from renewable resources like solar, biomass, wind, tidal, wave energy, and so on. And these infrastructure needs to be first developed and implemented to get a better grip on our green hydrogen works.
I think in this connection, I just wanted to share that yesterday's presentation, one of the speaker was talking about electrolyzers.
Yes.
different tests, what they have done in their labs.
Yeah.
Yeah. Shall we give up a send off? I mean, shall we wind it up?
Yes,
Yeah,
sir. Yes, sir.
sure. Anytime now.
Thank you very much, sir.
Thank
Thank
you,
you
sir.
so
Thank you,
much
sir.
for your wonderful session, sir.
Thank you. It's been an honor for me to interact with all of you.
Thank you, sir.
Yeah. Thank you, sir.
This STTP is actually jointly organized by me and Jiptesh sir, both of us. We both are good colleagues, are joined at the same time in this college.
Oh, okay.
Yeah,
Yes, sir.
and both are from
And
Dharma background.
This has been very close to me in my NIT Agartala days.
Very good, sir.
yes, sir. Even if now also, any
Yeah.
problem regarding the
I'm there for
any
you.
technical question, first feel free to call sir only, because
I'm there for
I know.
you always.
Yes, sir.
He's very close to me.
Thank you,
Thank you, sir.
Thank you, sir.
Thank you.
So, the participants, please stay back. The speakers can take break. Take leave for their lunch. Participant needs to stay back
Thank you,
and
sir.
fill feedback forms. Thank you, sir. Thank you
Sir,
very much.
namaste. Bye, sir.
Okay. So
Thank you.
I'll conclude and I'll move out of the session.
Yes,
Sir,
sir.
if possible, kindly share the PPT.
Sir,
Yeah,
Share.
I am sharing the Google Drive link to all the speakers through
Okay.
email. You
Okay.
can upload the PPT there, or you can directly share
Sure.
to Jivitesh, sir. Anything is fine.
Sure. No problem.
Thank
No
you, sir.
problem. I'll share it.
Thank you, sir.
Okay.
Thank you.
Thank you, sir.
Thank you.
Bye,
Bye.
sir.
Bye.
Participants needs to stay back. We are sending you the feedback link. Just wait. Just wait for a couple of minutes.
Where is sharing the link for that?
Just hang on. Just stay.
Please, all of you wait.
Thank you, Professor Dattatreya. Thank you very much. All of you fill the PPT, fill the feedback forms shared in the group, the chat box. Thank you, Dr. Ramesh, sir. I need everybody to fill the forms.